Hi, and welcome to the second project of aerodynamics. This project will focus on airfoil design tools and performance characterization and optimization. The design of airfoils has a little bit of an art to it, and defining their shape and what impacts their performance can be difficult. Often, engineers look for fast and efficient tools that can accurately tell them about the performance of a given aerodynamic shape. This lets them compare many different shapes and optimize for some desired output parameter. One tool that's widely used are panel method solvers, which we've studied in the past. In this project, a computer program called XFoil will take center stage that uses the Vortex Panel Method combined with a viscous flow, turbulence, and separation models to give accurate performance data. We're going to start the project by considering the NACA 4-digit series airfoils. Before there was standardization in profile design, early studies told us that the foil thickness and camber were two of the primary parameters that influence performance. So, NACA came along with standardization that defined these characteristics in one of the first sets of defined airfoil profiles. The numbers in the NACA profiles have meaning. Take, for example, the NACA 2412. The first two digits tell you about the camber, and the second two digits tell you about the thickness. Let's draw the foil and label the chord line and the camber line, both connecting the leading edge and trailing edge. The maximum thickness of the foil is controllable and is represented by the last two digits of the 4 in percent of chord. For example, our NACA 2412 has a maximum thickness that is 12% of the chord. Now, let's consider the camber. There are two important aspects of the camber that we can tweak. First, we have the maximum camber value, which is the max that the camber line deviates from the chord line. This is the first digit of the 4 in the NACA definition, and it is also in percent of chord. For example, our NACA 2412 has a maximum camber that is 2% of the chord. Second, on the camber we have the chordwise location that this peak occurs. This max camber location is the second of the 4 digits and is in tens of percent chord, meaning a NACA 2412 has a peak camber 40% of the way down the chord line. The 4 corresponds to 40%. And for the NACA 4-digit series, these are our control options. All of the other aspects of the surface and camber curve shapes are predefined and fixed. There is a special subset of NACA 4-digit foils, where the first two digits of the 4 are 0. This means the foil has no camber and is in line with the chord. These are called symmetric foils because they are symmetric across the chord. Generally, symmetric foils are not as good for steady aerodynamics at fixed angles of attack. However, they are great for surfaces that are moving up and down, like an unsteady foil, or need to be neutral, meaning no lift at 0 angle of attack, like control surfaces. And now that we have the foil shape down, at least for the NACA 4-digit series of foils, we can think a bit about what performance means. Typically, aerodynamicists care about the foil lift and drag as well as the moment about the quarter chord. So, when you look up the performance of various foils, you will see a lot of CL versus alpha, CD versus alpha, and CM versus alpha plots. In addition, there are other performance metrics to consider. For example, the lift to drag ratio, or CL divided by CD at a given angle of attack, is widely regarded as an important efficiency parameter for foils. You might also care about the maximum angle of attack before massive separation, near where the CL curve maxes out and starts to trend downwards. Depending on your situation, you'll value different things. We will explore all these parameters in the project. Now that we have our foil shape defined and performance metrics, let's open up XFoil. What you'll notice is that XFoil runs out of a command window type interface, delightfully old school. The way XFoil works is you type in different commands to change settings, load foils, or enter different command levels. The first thing you will do is load the foil. There are a number of foils built into XFoil, so right away we can look at one of our NACA foils that we're interested in. Let's use the NACA 2412, a popular foil which has 2% max camber. The max camber is 40% of the way down the cord, and the maximum thickness is 12% of the cord. Type in NACA 2412 and hit enter. It might not seem like much, but now we're working with a NACA foil in the background. If we type in the command ppar, we can see how the foil has been divided into segments in a new plot window. These segments are our panels for the panel method. From here, if we wanted, we could change the number of panels by typing first n, hitting enter, then entering a new number and hitting enter. We can try 199 here. Now, to back out of this environment, hit enter a few times until you see XFoil in the command line. From here, type OPER and hit enter to get into operation mode. You will notice now the command header says OPER. If we wanted, we could jump right into running a simulation. Type alpha 0 and hit enter. Note here alpha has an F. And with that we see our first plot. Here the pressure coefficient is plotted versus X, with two curves representing the top and bottom of the foil. We also have some numbers in the top right corner representing the foil lift coefficient in the moment. You might notice the foil drag is noticeably missing. This is because we have yet to set the flow to be viscous, and the Envisage solver cannot compute drag, at least viscous drag. So, let's turn on viscosity. In the command window, we should still be in our operational environment. Type VISC and hit enter. It asks you for a Reynolds number, which non-dimensionally represents the viscosity. Let's start with 3 million. Note here that you do have limits. You can't run too low of a Reynolds number with XFoil, or it will have trouble converging or giving you accurate results. You'll probably want to stay above 100,000 to be safe. Now that we've set our viscosity to be on, let's run the same angle of attack. Type alpha 0 and hit enter. Now, the curves get more colorful. We get more information. In the background, we still have the dashed lines which represent our Envisage approximation of the pressure, but we have the pressure for viscous flow as well. Below that, we also have lines going over our airfoil. These represent the approximated boundary layer height on the surface. It's in this boundary layer where viscosity is critical. And in the top right, we now have drag and L over D information that we didn't have before. Let's back out and try a more dramatic angle. In the command window, type alpha 18 and hit enter. Now, you might notice the command window seems a little less happy with us. This is because we tried to iterate to a solution for the panel vortex strengths while keeping the cutter condition, and it just couldn't make it happen in the number of iterations it tried. And that's because we're limiting ourselves right now to the default 10 iterations, which is really low. If we wanted to run 10 more, just hit exclamation to run another 10, and again, and again, and you might eventually converge to a solution. However, we can also set our iteration number to be much higher. Type ITER, hit enter, then 200 again and hit enter. This tells the simulation to try at most 200 iterations before giving up. Let's try that alpha 18 again. Type alpha 18 and hit enter. Uh-oh, it still didn't work. This is because we tried to jump from an alpha of 0 to an alpha of 18, and for this type of solver this is a big jump. In the background, the way XFoil works is its first guess at the iterative solution is the solution that it last had. So in this case, it last had a good alpha 0 solution, and it was trying to then use that to try to guess an alpha 18 solution. So sometimes it helps to build up slowly. So here, let's try alpha 14, see if we can get it to converge, and then we should also be able to get alpha 18 to converge. And look at that, we have the performance at a very dramatic angle of attack. Notice how that the boundary layer grows much more rapidly, and at some point, flow detaches completely from the foil. Generally, you want to avoid this massive separation because it comes with a very high drag penalty, which is why you generally don't try and fly NACA 2412s at 18 degrees angle of attack. Now this plot window is nice, but you might find it chopping values in weird locations. Let's export our data for this single case. In the command window, type cpwr. It will ask for a file name and give it a txt extension. In the folder with the XFoil, you will now have a text file with your prescribed file name. Open it up and you will see it has all the pressure distribution information for your foil neatly organized. This can be imported into MATLAB or Excel for more sophisticated plotting. So that covers running a single angle of attack, but what if we wanted to test under a specific range of angles? Let's open up XFoil again. Load the same NACA foil, type NACA 2412 and hit enter. PPAR is used to show the panels, N to redefine the panel number, and 199 panels should work. Type OPER to get into the operational hierarchy. VISC turns on the viscosity, which we set to 3 million again. ITER to change the iteration number, set that to 200. Now, run a simple alpha of 0 to make sure everything's working. Next, we want to tell XFoil to start saving the alphas that we test to another file. To do this, type PACC, which turns on point accumulation. It asks for a file name, and let's give that an txt extension. Hit enter again when it asks you to define a dump file, because we won't worry about that. Now, we can run a sequence of angles. Type ASEQ and hit enter. It asks you for the start angle in degrees, which we'll set to -10, then the max angle, which we'll set to 20, and in increments of 0.5 degrees. Hit enter and watch the action. It will cycle through all the angles and build up that text file in the background. Once everything's finished, hit enter twice, then type quit. Go to the parent folder and you'll notice a new text file. If we go to the folder that has XFoil, we'll notice a new text foil with our data in it. Open it up to find the force and moment coefficients, along with the lift to drag ratio, all neatly organized against the angle of attack. This can be imported into MATLAB or Excel for advanced plotting. And that's it for the first portion of the project. This should get you through the majority of the tasks. However, the last task deals with working with custom airfoils. Maybe you don't care about NACA foils and you want to work with a Clark Y, N22, or something else. Well, we're in luck. XFoil lets you load any profile you want within reason, as long as you can put it into a data file at a certain way. For this, I've made a MATLAB function to save foil profiles, but first, let's consider how to define arbitrary foil shapes that don't belong to specific families like NACA or Clark. In my research, I do a lot of studying of fish and swimming mammals and their fins. Unfortunately, nature hasn't evolved to use only a specific type of foil, and a lot of them are organic and seemingly random. So, I made a tool that can build any foil shape with a few parameters. To do this, I took all of the foils that I could find, organized them into a library, and conducted singular value decomposition on that library. There's a very mathy way to explain singular value decomposition, but I'm certainly not qualified to do it. However, I do have a physical interpretation I like to use to understand it. Say you have a built Lego set. That set has many different Lego types and bricks, all placed in very particular spots. Now, if you disassembled that set into piles of each brick type, you could count how many of each brick you needed to make that set. For example, maybe you needed 10 long red bricks but only 3 short blue ones. When you disassembled that set and counted the bricks, you did what singular value decomposition is doing to the airfoil library. It identified the most common surface profile shapes that exist in building a curve that looks like an airfoil, then counts how much of each shape we needed to construct any single foil. Instead of a count, though, we have what are called coefficients. These coefficients multiply the shapes, which we call modes. Sum up the product of all the modes and their coefficients, and we have an airfoil. The benefit of this is we can define many airfoil profiles with complete customization with only a few numbers. With 4 coefficients, we can make almost any foil you can think of. And if you need to, you can always add more brick types, meaning more modes and coefficients. I've provided a MATLAB function and a MATLAB sample script that define the shape parameters, plots, and saves the foil in the necessary format. Open the sample script with the FoilMaker function in the same directory. And let's define some coefficients. The way I've designed it, if you choose all 4 shape coefficients A through D to be 1, you've approximated a NACA foil with a 12% thickness. If you change these coefficients, you change the shape. Play around with it and get a feel for how sensitive each coefficient is to changing the shape. Keep in mind, small shape changes can result in dramatic performance changes. Now, we can define the camber. Here, I've adopted the same strategy as the NACA series foils, where we define the max height of the camber and the X location of that peak. With these 4 shape coefficients and 2 camber numbers to define, that leaves us able to define almost any foil with 6 numbers. Let's make a random foil and test it out. Pick some numbers that are within reason, hit play, and it will save our foil for us in our directory. Open XFoil. Now, the first thing you will need to do is load our new foil. Hit load and it will ask for a file name. Once it's loaded, it will ask you to name it, but you don't have to. Now we can run it through the same process as the NACA foils. Here, I'm using the PANE command to smooth out the profile shape with an automatic function in XFoil. This is good to use if you're bringing in some kind of unknown shape that might not be optimized for XFoil the way NACA was. Let's enter operation mode, add viscosity, change the iteration number, and test out a single or range of attack angles. And that's it. You can now test custom foils with XFoil. One of the beauties of having the ability to customize the foil shape is it means we can also optimize it. Now, for this project we cannot do true optimization. That takes a lot of effort to get another program to interact with XFoil and run it in a feedback loop. But we can do a few manual iterations of an optimization with you, the student, as the optimizer and communication. First, let's do a basic overview of optimization. Our goal today will be to optimize the foil shape for a certain flight condition and desired performance. In optimization, you generally are altering some input to get some desired output. You try an input, look at the output, see how far you are from your desired output, and run some new inputs. Iterate until the desired output is achieved. What we're going to employ today is a hill climbing technique. Picture a person on a hill. This person's goal is to get to the peak of that hill. Their inputs here are the ability to step to the right or to the left. Their output is the altitude, and if they want to get to the top of the hill, then they have to maximize their altitude. It might seem pretty easy how a human could find the top of the hill, but what if you had to explain the procedure very basically to a robot? First, you would assess your current standing location. Call this altitude 0. Then, try and take a step to the right and note your altitude. Then a step to the left and note the other altitude. Now, you will want to compare the 3 pieces of information you have. Was a step to the right greater than the original position? And greater than the left position? How about a step to the left? From here, you have 3 choices. You can step right, step left, or stay put. You choose based on your altitude information that you just tested. If stepping in one direction was best, you step in that direction, call it your new current location, and loop through the process until you eventually choose to stay. Once you choose to stay, you now have found at least a local hill peak. It's not perfect or efficient. There are much better optimization strategies out there, but this gets you to the top of the hill eventually. This is easy enough for one parameter, but what if you have lots more? You do the same procedure, but for each input type or dimension. Consider a point in 3D space, and it has the ability to step in 3 separate directions, so 3 inputs. First, you step in each direction separately. Then, you assess your best step in each direction. Finally, you move your location to the new location, meaning you take the best step in all 3 directions. This is your new location where you can run another iteration. Let's show it with a dot. Step forward and backward in X, then step forward and backward in Y, then forward and backward in Z. Determine the 3 best steps in each direction and move your dot to a new location in the 3-dimensional space. The next iteration, you would do this all over again in that new location until you reach your desired output. In our case for the project, we want to optimize the foil shape for a given condition and desired performance characteristic. The foil shape coefficients and camber definition are our input parameters. Our outputs consist of the lift, drag, moments, and so on. Your desired output is up to you. For example, you could choose to maximize the lift at a certain angle of attack. When you optimize by hand, like how we will be doing, we will be limited to only a few iterations and it won't find a true optimum. However, you can still get a bit better performing foil shape than where you started while learning of the basics of optimization. To see an example of how I did the brute force optimization, follow along the next segment. It might help to make an Excel spreadsheet like I did, open up all 3 programs MATLAB, XFoil, and Excel, and keep track of the performance and determining the next best step. I hope you enjoy the rest of the video and also enjoy the project.